So, good morning, good afternoon, good evening, depends on where you are in the world. Thank you to join us for this very interesting talk that we are going to have today by Professor Vidya Chhabria. But before giving the floor to her, I would like to do some announcements. So, if you lost the talks that were being done since 2020, so you can see all the talks that are recorded and available in this YouTube channel. So it's about 150 talks that you can choose with great speakers. No? And also, I would like to invite you to participate in the Cadathlon Brazil. So the winners of the Cadathlon Brazil were invited to participate in the Cadathlon connected to ICCAD. So the next Cadathlon Brazil will be in July 24 in the beautiful city of Maceió in the northeast of Brazil. So you have till 20 June to do your registration. And if you don't need to know much in microelectronics, but you need to be good in algorithms and programming, and then you are going to have the skills to solve the problems that will be proposed. So don't lose this very nice opportunity. Then the SBCCI, the deadline has already finished. The selection of papers should be announced today. And anyway, you are invited to attend this very special edition as part of the Chip in the Jungle and the workshop on circuit and system and the student forum. The call for paper deadline is still open. So this is a great opportunity to go to a very nice location. And this year, SBCCI got 50% more papers submitted than the last 2 years now. And by the end of, so the main conference will be in Manaus in the Studio 5 Conference Center. And then we have extension in a hotel in the jungle, a very nice location. And it's a program with all inclusive. And we are going to have also a technical panel there. But most of the time is to do some tours in the jungle and a very nice program that is already set up. And to guarantee your room there, you should do your registration by June 15. And we still have about 8 days to submit your papers to VLSI SOC. That, as you know, it's a IEEE and IFIP conference that goes around the world. So this year is in Chile, South Chile, so a very nice location. And then we still have time to submit your papers. And also together we have the PhD student forum and student forum also. And with the grants for students. So one grant that is given by IFIP to students from emerging countries. And also there is a student travel grant from CASS and also from Calcium EDA. Then next to LASCAS, so the flagship conference of CASS organized each year in Latin America. That means an international conference of CASS in Latin America. Next edition is in Arequipa, Peru, and you have till beginning of September to submit your papers. And as usual, together we have IberChip, that is a workshop where you can also submit the papers not only in English but also in Spanish or Portuguese. So for the ones that are starting the field, is a good opportunity to submit their work and also to attend the LASCAS. And LASCAS 2027 will be in Panama, also a very nice location to go, as you can see by some photos here. But today we are here to attend the talk by Professor Vidya Chhabria from Arizona State University. talking about AI for physical design, overcoming EDA bottlenecks in optimization, analysis, and automation. So Vidya is an assistant professor in the School of Electrical, Computer, and Energy Engineering at Arizona State University. She graduated with her PhD and master degrees from the University of Minnesota in 2022 and 18, respectively. Her research interests lie in computer-aided design for various size systems and primarily resolve around the physical design, optimization, and analysis algorithms. She has received the ICCAD Best Paper Award in 2021, the University of Minnesota Graduate School's Best Dissertation Award in the Physical Science, Mathematics, and Engineering category for 2024. She's currently the IEEE Council EDA DATC chair and has served on several conference, TPCs, and organizations committee. Her current research explores the application of machine learning algorithms for electronic design automation and environmentally sustainable computing. So thank you very much, Vidya, to accept our invitation. And the floor is with you to start your presentation.
Thank you for the kind introduction, and thank you, Professor Reyes, for the opportunity to present here with the IEEE CASS. Uh, so today, my talk is going to be about AI for physical design, overcoming EDA bottlenecks in optimization, analysis, and automation. So EDA itself is an area that builds algorithms or software to design chips, and chips for decades now have been growing in complexity. We started at having tens of transistors on a chip to today having billion, if not trillions, of transistors on a chip. Both Moore's law and EDA have contributed to enabling the growth of this growth in complexity of today's chips. EDA has enabled us to move away from manual design of circuits and layouts by hand to automatically designing, optimizing, and analyzing large circuits. However, with the end of Dennard scaling, things have become much harder for Moore's law to sustain. Yes, the number of transistors is still growing at that exponential rate, but the number of useful transistors on the chip that help us improve performance has not increased at the same rate, showing a significant slowdown in Moore's law. The advent of high compute demanding tasks such as AI have made things a lot more challenging. For example, the complexity of machine learning models have been growing exponentially towards this path for better accuracy. And the picture here shows that since 2012, that was the year AlexNet had its success on ImageNet dataset, the amount of compute required in the largest AI training runs has been increasing exponentially with the 3.4-month doubling time. And this does not even include our latest large language models. This picture is old. Since 2012, that metric has grown by over 300,000 times. So what I want to say here is I want to bring in that picture from the previous slide and align the time axis. Even though the y-axis is not the same here, my message here is previously Moore's law had a 2-year doubling time, which was allowing hardware to keep pace with these growing demands of software. However, there's not only been a slowdown in Moore's law in the recent past for the past decade, but there's also been the boom of AI, which has created these large demands. So if you thought this gap created by the slowdown of Moore's law was bad, known as the design capability gap, just look at how big of a gap AI demands have created. So we need hardware, or we need chips that are far beyond today's capabilities in order to sustain these AI demands. One way to create such hardware, and one way what our research group looks at, is can we build significantly better EDA tools to help us close the gap between, close both the design capability gap and the gap AI demands have created. So the question here is, why is this happening? What are the challenges EDA has posed to the semiconductor industry? And today I'm going to talk about 4 challenges. The first challenge here is the scale, or the problem of N in EDA, or electronic design automation. Most algorithms that perform synthesis or place and route of all these transistors on the chip, verification or analysis, are all polynomial in N, where N is the number of transistors. So if we go from billions to trillions of transistors, and we have algorithms that are quadratic or logarithmic in complexity, it makes the sustainable use of EDA tools extremely challenging. And there is a runtime problem, which has therefore led to an increased time to market of today's chips. The third challenge here is a productivity challenge. Since today's EDA tools are based on heuristics and they often trade off speed for accuracy, there's a lot of manual intervention and expertise that's required for high quality design, where we want to extract every ounce of quality of results or power performance area that we can. And as a result of these three challenges, we have a fourth challenge. And that fourth challenge here is the challenge of cost. And it's not just cost in terms of dollar, but it's a cost in terms of risk, expertise, which are all created barriers to entry in the semiconductor design or IC design space. So, what I'll be talking about is today's presentation is EDA and EDA in the context of physical design. And that is the flow that's shown on the left here. The physical design flow takes RTL, or a hardware or a description of hardware in Verilog, and takes it all the way down to GDS in digital designs. And GDS is what goes finally for tape out to the fab. So this is the realm of problems I will be talking. This is the scope and different kinds of problems in this scope that I'll be talking about. When I think about EDA algorithms for physical design, there are three things that come to my mind: automation, analysis, and optimizations. However, the EDA tools that perform these automation, analysis, and optimizations, these have all those challenges that I described on the previous slide. There's a challenge of scale, there's the challenge of time to market, there's the productivity challenge, and there's also the cost challenge. In some of our research that we do in our group, in our experience, we say that AI or ML can help address some of these challenges. And I think AI or ML plays a very crucial role in addressing these challenges and improving EDA tools, particularly when we look at goals such as, we wanted 24 hours, no human in the loop, no power performance area loss for this physical design cycle. That can be AI inside EDA tools, AI around existing EDA tool flows, or even AI that serves as chatbots or design assistants in today's world. Those can help improve productivity. Those can incorporate automation. AI inside EDA tools can help with optimizations, and AI around EDA tools can also help with analysis. And I'll talk about one example in each of these categories today in the rest of my presentation. I'll talk about one example for automation, one for analysis, and one for optimization. So here is a quick overview of what I'll be talking about. So over the course of this talk, as I mentioned, I'll give a few examples of how AI and ML has played a role in automation, analysis, and optimization. These days, you cannot have an AI talk and not talk about LLMs. So the first example I'll give is how LLMs are helping in automating various physical design tasks via the development of chatbots or EDA tool assistants. The second example I will give is how AI can help with some analysis. In particular, I'll talk about IR drop analysis or power delivery network analysis. And I'll also talk about how AI can help with thermal analysis. And this is using image-based AI. The first used text-based AI or large language models. The second here is using image-based AI. And in the third one, I will talk about how AI can help with optimization at the gate level netlist. So timing optimization and power optimization, where the circuit itself is represented as a graph, and we can leverage graph neural networks and reinforcement learning to perform this optimization. So one thing that I particularly want to convey with this slide is that it conveys it highlights different kinds of modalities that physical design data contains. And one of the key tasks of applying AI to any physical design problem is being able to map that EDA problem or that physical design problem into something that AI can solve. So basically bring that problem into a modality that AI understands. So for instance, here AI understands text. So we're trying to generate scripts. We're trying to parse tool reports. Here AI understands images with convolutional neural networks. So we have mapped the IR drop and thermal analysis problems into an image-like problem. And AI also has found success with graphs, with graph neural networks. So we've mapped the optimization or the gate level timing optimization problem into a graph classification problem or a graph problem, and we use graph neural networks to solve it. So I want to highlight the different modalities, and the key idea here is mapping the EDA problem to one of these modalities and then leveraging advances in AI to solve that EDA problem. So over the course of this presentation, I'll be using this as an outline slide. I'll be starting with one example in automation, then going to analysis, and then optimization. So first, let's get into the automation part using large language models. There have been several works already that actually incorporate LLMs into the chip design field, and here are a few notable examples. You can notice that most of these papers that I've listed here are related to RTL design or synthesis, or the front end part of an ASIC flow. And the advantage of using LLMs there to solve RTL or synthesis problems is that RTL languages are open languages, not restricted by licenses, making it easier to prepare data for LLM related work. However, when we try to prepare data for LLM related work in physical design, it's significantly more challenging. Commercial physical design tools are limited by end user license agreement, PDKs are behind NDAs. What's more challenging is that with commercial design tools, all the APIs are closed source APIs, which cannot be fed into ChatGPT, for example. And these drawbacks are restrictions that create significant barriers to applying LLM in the physical design field. However, open source EDA and open source PDKs, open source EDA tools and open source PDKs have provided a path towards addressing a lot of these barriers. One example that I would like to give here is this of an open source EDA tool chain is OpenRoad, which does the physical design flow RTL all the way to GDS. And I'll be using this tool in various aspects of the work that I talk about for the rest of the slide. And the advantage here is that there are no license restrictions. There are no you can work with open source PDKs within this world, and it allows us to overcome the barriers that are listed on the left here. So if you think about physical design and LLM related efforts, before we proposed this work of developing an assistant or a chatbot, there were two other works that did the same. One of them is what's known as Chat EDA from the Chinese University of Hong Kong, presented in MLCAD 2 years ago. And it uses a Llama 2 based model to do physical design task planning and generate scripts for each task. The work generates scripts for open source physical design tools like IEDA and OpenRoad. The second one here is ChipNemo, and this is from NVIDIA. This as well uses a Llama 2 based model, and it does several different tasks. One of which that's closely related to physical design is generating scripts for physical design static timing analysis. They have a 24 billion tokens of training, massive GPU runtimes, and all with proprietary data. And this kind of research is completely inaccessible to academia or smaller research groups. So, despite the effort that these two prior works for LLMs in physical design have put in, they have limitations. For example, the Chat EDA generated scripts at a really high level for physical design. It was not native scripts for an EDA tool such as OpenRoad or IEDA. ChipNemo's data and model are publicly unavailable for us to experiment with. So, therefore, looking at these limitations, we thought it would be nice to have an open source chat bot to work with OpenRoad to be able to generate scripts and answer question and answers, and to address those issues of of lack of data. And we created this open data set, or an open source data set known as EDA corpus for physical design, and it consists of two categories of data. It consists of prompts and scripts that are shown on the left here, and it also consists of question and answers that are shown on the right here. This was released and made publicly accessible with over 1,000 prompt script pairs and 600 question and answers pairs, all for OpenRoad. And it consists of questions, answers such as these here, prompt scripts pairs that interact with the database to perform a specific task or to perform various physical design challenges. Creating this data set itself was not easy. It was a tremendous amount of manual work that went in. The way this data set was created is it was scraped a lot of question and answers from OpenRoad's GitHub issues, pull requests, and discussions. We created it in a structured format where we have one specific prompt and its corresponding answer, or one specific prompt and its corresponding label. OpenRoad experts have worked towards gathering that data from GitHub and OpenRoad documentation, and then populated it within our EDA corpus. Prompt and script pairs have come from engineering coding contributions from a lot of graduate students here at ASU to create that EDA corpus database. This is basically a graduate student says, I want to extract all the pins or all the IO pins from my design, and then they write a script to do that within OpenRoad. And various graduate students come up with different tasks and they write different scripts, and it all becomes a part of the EDA corpus. It wasn't easy to do this because you also need to filter a lot bad data. For example, if you look at GitHub, there was a question on the issues or a discussion that says open road crashes during clock tree synthesis, what's going wrong? And a response to that was, hey, this is fixed in pull request 522. Just imagine asking a chatbot, hey, open road crashes during CTS, and the chatbot gives you a response saying, hey, this issue was fixed in PR 522, or closing this issue because it's stale, or I don't see this anymore, this must be an old version. So this is the kind of data that we had to get rid of, and filter out the bad data to be able to create that good corpus data set. We had some data augmentation techniques as well within the EDA corpus, where we scale the data set based on paraphrasing prompts using LLMs for both the question answers and the prompt script pairs. And we also change variables in the script names within the scripts to enhance or augment the data set completely. This gives us more data points, and it's more stable when you train these large language models using this data set. So using this data set, what we proposed is this chatbot known as Open Road Assistant. And the way we trained Open Road Assistant is we used this approach known as QLoRa, or a quantized low rank adaptation. It's a method in which you can train existing foundational models by adding weights or additional layers and attach them to the original model. And you're basically fine tuning only those additional layers that you've added. So it lowers the cost of training and it lowers the amount of data that you require. So I'll use a diagram to explain the process of Open Road Assistant training now. So in Open Road Assistant, the training flow, we use the EDA corpus data set that I talked about earlier, and we filter out unique data points. Remember, I also mentioned that we augmented the data. So first, we filter out all the unique data points so that we can create a test set that is not seen during training. In addition to that, we create a RAG database, and I'll come to what that RAG database is in a bit. But RAG essentially stands for Retrieval Augmented Generation. And a simple way to think about what happens in RAG is that the RAG model is able to look at this database and find the context or find text within the database that is most similar to a prompt or the most relevant context to the prompt that a user is asking. It does this by using metrics such as cosine similarity or semantic similarity metrics, and other semantic similarity metrics. So after gathering these two data sets, what we do is we create a RAFT-like technique. RAFT is retrieval augmented fine-tuning, where we get a prompt from the user. That prompt is also fed into the RAG database, which extracts the most relevant context. With the prompt and that retrieved context, we then create this new data set known as the RAFT dataset, or the retrieval augmented fine-tuning dataset. And using this RAFT dataset, we then train our two adapters that we had on an existing Llama 3 8 billion model, foundation model. And we noticed that the RAFT-like technique is useful because the RAG database prevents, the RAG and the retrieval model here prevents hallucinations, while the generative model of this Llama enables us to generalize across different answers. So once we've done that, we do this for both the prompt script generation as well as the question and answer generation. But for question and answer, we also have to do a few additional steps. We also hand pick context and prompts and paraphrase certain answers from the EDA corpus dataset. And we also have further additional instruction dataset, instruction fine-tuning of the Llama 3 billion work. This was required to improve the accuracy and correctness of our question and answers, question and answering assistant in this model. So this was the entire training process. I mentioned that I'll talk a little bit more about the RAG database here, and this is an example of the RAG database. The slide shows details of our RAG database for the script generation task here. For the script generation task, the RAG database is built on two kinds of data. The first is we have a list of about 400 to 500 APIs within OpenRoad, and we describe those APIs in terms of the function names, the arguments, and the return types, and a small text-based description of what the API does. We also have some kind of template code, because a lot of times with physical design, you're performing tasks that you perform repeatedly. For example, I want to floor plan this design. I want to route this design. I want to place this design. So the template of the code to place and route is used repeatedly across multiple users. So we have some template description of how to route or how to do placement in OpenRoad. So this is the API list is one part of the RAG database, and another is the template code. And based on the mapping, based on the retrieval context and the prompt, you get context and you can rank them from 1 to n. For the question and answers, we use the OpenRoad README files from GitHub as the RAG database, and that as well is sort of cropped into a size that's reasonable for the retrieval model, and we're able to rank them based on the prompt that the user provides in terms of cosine similarity. So once we've had that entire model trained, when training is complete, we now have to evaluate that model. So how does evaluation really work? A user will pass a prompt to the model. The OpenRoad assistant will first find the top 3 contexts from the RAG database. It will then concatenate the context with the question or the prompt together and pass that into OpenRoad assistant, which will then generate an answer or a script for that particular question. So here's an example of how this works. The script generation here shows how we can generate scripts for querying data from the OpenRoad database. So the question here is get every pin from the design and put them in a Python list. So then the model goes to the RAG database, extracts the APIs, the relevant APIs for that question. It then generates, the OpenRoad assistant then generates the script to perform that specific task. So this is like a one-shot generation, but then the question asked is what happens, the question that comes in is what happens if there's an error in what the OpenRoad assistant generates. So to solve that issue, we further extended this work to build this idea known as OpenRoad agent, or it's a framework for the LLM or the agent to interact with OpenRoad. In OpenRoad assistant, that is in this previous work here, if the agent generates an error message, then the user has to debug that error message and figure out what's going on by looking at the documentation of OpenRoad on what's happening, which sometimes creates a barrier to entry for newer users or naive students who are first time trying to use OpenRoad. So in that context, what we did is we created this agent framework where the LLM interacts with OpenRoad directly. And if the OpenRoad generates an error message, that error message is fed back into the LLM, which is then updated to fix that error message and pass that back into OpenRoad, and it keeps iterating like this without the need of a human intervention. So this work is known as OpenRoad Agent. It was recently accepted into this conference known as ICLAG. And this is set up for that agent, but I just want to show you this picture here, where notice that the user gives a question here called as swap master of instance so-and-so. It's basically asking it to change the standard cell type of a specific instance. The first time the model, the LLM generates a script like this, and it has an error in the script, and OpenRoad throws a message saying, hey, there is some kind of an error. There's no API known as find master with design object. So then that error message is fed back into the agent, and then OpenRoad, and then the agent updates it to say get DB find master. And then there is still an error which says you've capitalized DB, but did you really mean get DB? And then the agent updates that further and finally generates the right script. And this is without any kind of human intervention. So to evaluate both OpenRoad Assistant and OpenRoad Agent, we use these metrics known as pass at 1 and pass at k, or how many inferences does it take to generate a correct script. So if we're saying pass at 1, we're allowing only for one inference, and we're checking whether the script generated is correct or wrong, and it runs within OpenRoad without any errors and gives the result that we want. So with OpenRoad Assistant, we noticed that we had about 75% of an accuracy if you look at the stop line here. And that was better than other baseline models which weren't fine-tuned using EDA corpus, or which were fine-tuned but they didn't have Raft, or they had different adulation studies. But OpenRoad Assistant was only able to give us 75% for pass at 1, and a little bit more for pass at 3, maybe 78 or 80%. But what we went ahead and did was with OpenRoad Agent, with that iterative feedback, we noticed that that 70% or 75% jumped all the way to 94%, because the model was able to learn from the mistakes and the error messages that OpenRoad was able to give back information to. So it's a completed automated agent framework to generate scripts for various physical design tasks. OpenRoad Assistant, OpenRoad Agent, EDA corpus, they're all open source. The models are available on Hugging Face. And here are some QR codes in case this is of interest. Okay, so that was the first problem that I wanted to talk about, which is automation, and it essentially helps improve productivity. It lowers the barrier to entry for a new student who wants to use OpenRoad or use this EDA tool, because EDA tools in general could be really overwhelming, have several parameters, and it's nice to have some assistant or an agent to help you perform various tasks, and you can talk with it using natural language. And that was the goal of this specific work, to enable automation of various physical design tasks, lower the barriers to entry for new users of EDA tools. So moving on to analysis. And in analysis, I want to talk about two kinds of analysis. Analysis itself in EDA, in the realm of physical design, and EDA for physical design, is extremely computationally challenging. So the two analysis I want to talk about here is IR drop analysis, and the other is thermal analysis. IR drop analysis, or PDN analysis, is the process of computing voltage drop or IR drop on the chip due to parasitics of the power delivery network itself. The power delivery network, or the PDN, consists of wires that carry voltage from the bump all the way down to the standard cell in the design. Right? So when you carry voltage from the bump to the standard cell, there are some voltage drop that occurs due to the R and C of the wires of the power delivery network itself. And you want the voltage drop at these standard cells to be greater than certain limits in order for the standard cell to be able to perform at the speed that it's required, or with the correct functionality that's required. So what we do in EDA is we take this power grid and we model it as a circuit of RC, voltage sources and current sources, where the bumps are voltage sources that bring in the voltage from the external part of the chip. The cells, whenever they switch, they draw current. So they are modeled as current sources that are shown over here. And the wires, they're parasitic, so they're essentially modeled as RC. So now the goal is to solve this circuit, this really large circuit over here, to compute the voltage drop at every standard cell. Solving this in steady state amounts to solving a large system of equations of the form GV is equal to J. And it's large. This system has billions of variables because there are billions of nodes in this system that are shown here. And it's computationally very expensive to solve this GV is equal to J system, because you have to invert this G matrix to get your voltage values. So this is the challenge with power delivery network analysis. Another analysis, which is thermal analysis, is algorithmically very similar to power delivery network analysis, but it's also equally important as IR drop analysis. And thermal analysis essentially measures on-chip temperature. Conventionally, the way you do thermal analysis is you solve this set of partial differential equations shown on the screen here. So for a computer to solve this partial differential equation, it has to perform numerical integration for transient analysis. And in steady state, it has to also maps onto a large system of equations like this of the form GT is equal to P. Whenever you're performing numerical integration, or when you're solving these large system of equations, you need to use an FDM-based approach. And the more variables that you have with an FDM approach, it's computationally very expensive to solve. And in fact, we found that it takes hours of runtime to solve this partial differential equations on industry scale size designs. So the idea was, can we save time by using AI approaches for this problem? So on this slide here, I've presented a very equation-heavy view of these two problems of IR drop analysis and thermal analysis. But on the next slide here, I want to present a more visual representation of the same problem. So this is the problem of thermal analysis, where the input is a two-dimensional distribution of power, and the output is a two-dimensional distribution of temperature. Both these images or maps here are correlated, but they're not identical. The correlation is that in the region that has high power also tends to have high temperature. And this is the kind of relationship a neural network can very easily capture. In particular, what we proposed is that we use fully convolutional neural networks for this problem by mapping this thermal analysis problem into an image-to-image translation task. In this case, we use this neural network known as a UNet, which has found immense success in image segmentation problems in the AI world. And the idea here is that for the thermal analysis task, we are classifying every pixel in the power map to a corresponding intensity level of temperature. One of the advantages that the UNet provides, or the fully convolutional nature of the UNet provide, means it has no fully connected layers. And this makes the UNet input image size independent. And if it's input image size independent, it can transfer to different chips of different sizes, of different areas. And it can also transfer to different technologies with a little bit of fine tuning. So once this model is trained, it can be used to predict thermal profiles on various unseen designs, provided you give it an input power map. So this is an example of the static thermal analysis problem. And for the transient analysis problem, the input is a time varying series of power distributions, which is shown here, or a video of power distributions. And the output is a video of temperature distributions shown here. So instead of an image to image translation task like we did in the static case, for transient thermal analysis, we converted to a sequence to sequence translation task. And the core architecture here of the model that we use is very similar with the encoder and decoder, except that we also use LSTMs, or long short term memories, to incorporate the time series dependence of the transient analysis problem, or the video like nature of this problem. So what we did is we trained these models using a large training data set, and then we were able to transfer the model or use the model during inference to generate a predicted temperature on various unseen power distributions. And we noticed that the ground truth temperature, by solving that large system of by solving those second order partial differential equations, and the predicted temperature were very close. And we did this inference in a matter of few milliseconds. So we essentially brought down that runtime of several hours to a few milliseconds by training this machine learning model and then performing inference, essentially a data driven technique for the thermal analysis problem. I only presented the thermal analysis problem here, even though I have IR drop analysis, but fundamentally they are both similar, where we did the same for static IR drop as well as the same for transient IR drop. We just had more types of images and different types of images for the IR drop problem than we did for the thermal problem. Okay. So I presented two techniques, one for AI for automation that leveraged large language models. I also presented AI for analysis that leveraged image-based techniques such as convolutional neural networks and long short-term memories for automation and analysis each. So this was an image-based approach. This was a text-based approach. I'm going to pause here to see if there are any questions before I move on to optimization. I know, because I've been talking constantly for 30 minutes. I hope I didn't bore all of you, but I'm going to pause here to see if there are any questions. I'm happy to answer. If not, I'll move on to optimization. So one of the questions here is, could you please comment on hardware resource needs and runtime needs for training ML model for transient thermal analysis? Sure. So this was work that I did in 2021, so it's been a long time. For this particular paper, I think we had about thousands of different power profiles, 1,800 to 1,000, if I remember correctly. The model, the data had come from Qualcomm for this. We had training times in the order of 6 to 7 hours. Those days, we were looking at lower end GPUs, and we also had only about 800 data points. The training time will include two types of training. It includes one, I mean, the training of the machine learning model itself, but then there's also the time taken to generate the data. So of course, the time taken to generate the data is much longer than the time it took to train the model, because for generating the data, you have to take these power distributions and actually solve them using a ground truth solver. So that took a lot of time, but for training the machine learning model, I think it was 6 to 7 hours for 800 data points. Thanks, Jose, for the question. So there's another question from Rishir, Nikhil. Have you tried different models and what is the effect? Yes. During my experimentation, this was when I was a PhD student at the University of Minnesota, we tried different models. We tried conventional convolutional neural networks. We tried I think there was XGBoost. We tried all of those, and I think we ended up with this particular model, which had the highest accuracy. I don't have the numbers on these slides on how each of those performed, but that was something that we had done when I was a PhD student, and I'm happy to pull out that data if I can find it at some point. I hope that answers your question, Rishabh.
Vidya, maybe you can leave the questions for the end of your talk.
Sure, no problem. I had extra 5 minutes, so I thought I could
Mhm.
ask questions. I mean, I could take some questions in case there were pressing questions. Sure. So now I'll move on to optimization. I've spent about 5 to 10 minutes here, and then we'll have more time for questions. So this is the optimization here. I'm talking about netlist level optimization, timing optimization, power optimization at the gate level, netlist level. So to show an example of how AI can help with that problem, I'm going to use uh, this problem known as engineering change orders, or ECOs, and ECOs that are performed to overcome to fix a timing violation that is induced by IR drop. So I already talked about what IR drop is. It's the voltage drop through the power delivery network. And if you don't get ideal voltage at the standard cell, then the time it takes for the standard cell to switch is going to be slower. And because the delay increases, that could induce a timing violation because of the impact of IR drop. So to motivate this problem, I'm going to talk about the physical design flow a little bit. So typically at the floor plan stage, you build your power grid after you've placed your macros, right? You place your macros, build your power grid. Then you check whether your power grid is good. You have some voltage drop and electromigration limit checks. You analyze the power grid. You then perform placement of standard cells, routing of standard cells to reach the sign off stage. And because you've changed the design a little bit once you've placed and routed, you want to rerun IR drop analysis. So you will rerun IR drop analysis at the sign off stage to get a voltage map. And you might notice that, hey, IR drops were good at this stage, but once I've come here, there's some excessive IR drops in different parts of the design. So now you need to, these excessive IR drops is leading to a timing violation because there's lower voltage at these particular cells, so the delay of those cells has increased. And to fix these timing violations that are induced by IR drop, what designers typically do is they perform ECOs, or engineering change orders, where they now have to size particular gates, or they have to optimize the design to overcome that timing violation that's induced by IR drop. And since it's the end part of the design cycle, it's near the sign off stage, you don't want to make big changes. You want to make a small perturbation to the design in order to be able to fix that, because if you make a big perturbation, you need to go back and redo your entire design flow. So, in the context of this problem, the perturbation that you can do, one of the perturbations that you can do to fix the timing violation is known as gate sizing. I can change the size of these logic gates to fix the timing violation that's induced due to IR drop. And that's where we have applied AI techniques to help this ECO problem. So the goal of this optimization problem is to fix the IR drop induced timing violations using logic gate sizing. So this work that we had proposed at MLCAT 2024, it had three key contributions. One is it's addressing this interaction between IR drop and logic gate sizing, which has not been fully formally addressed in the past. Second is we apply reinforcement learning to this problem, but there have been other approaches that have applied reinforcement learning to the gate sizing problem, but they have really large runtimes, and it's because they apply it to the complete netlist. The solution space of that optimization problem is massive, and reinforcement learning doesn't scale very well. So in this particular work, we show that RL is suitable for a small limited search space problem when we're talking about an ECO problem that's local to a particular part of the netlist or the layout. And typically, with traditional RL techniques, if you look at the reward function, it's a multi-objective reward function. You usually have some kind of weighted sum in the reward function. But finding the weights of every term in the multi-objective reward or the multi-objective optimization is a very hard problem. So what we do is we combine prior non-ML era knowledge to enhance reinforcement learning using insights from traditional solvers such as Lagrangian multipliers and Lagrangian relaxation to find the exact objective weights for the reward function in RL. So I'll talk a little bit more about detail in each of these tasks. So the optimization problem here is set up as a constraint optimization problem where we want to minimize the total power and we want to meet the slack constraints. So if we go back and look at this power versus delay trade-off curves, The purple line here shows the power and delay trade-off curve without IR drop annotated. And the red line here shows the power and delay trade-off curves with IR drop being annotated. So if you notice, for a fixed amount of power, without IR drop, you have about a lower delay. But with IR drop coming into picture, the delay becomes much higher. And then there is also a power overhead if you look at it from the other direction. So the goal is to solve this optimization problem. Traditionally, this optimization problem for logic gate sizing is solved using Lagrangian relaxation, and it can be mapped onto an LR or Lagrangian relaxation problem. So you convert this constraint optimization problem into a Lagrangian objective function where the multipliers, these lambda terms, are obtained using bias optimization theory rather than some ad hoc fine tuning. However, traditionally, LR-based techniques, they're really slow and heuristic-based that could sometimes lead to suboptimal solutions. So to overcome these challenges, what this work does is it uses reinforcement learning-based techniques to improve the quality of the solution. And to do this, we convert this logic gate sizing problem. We map this logic gate sizing problem into a graph problem. So the first thing is we take the entire circuit netlist here and we map it into a graphical representation where every node is annotated with the list of features that are shown here. Next, we have an agent or a GCN that next we extract a state from this graph. And when I state, I mean is we extract a part of this graph that has slack less than 0 and a neighborhood of that part of the graph, a two-hop neighborhood of that graph which has slack less than 0. So essentially, I find all the timing paths in my netlist that have slack less than 0 and look at a two-hop neighborhood of that graph to get a local graph that I can then apply my reinforcement learning technique to. This is what is known as the state in RL. We use this state, use an agent known as a GCN, which is a deep neural network model, to perform an action on that particular state. And in this case, the action is to select a particular gate and either upsize or downsize it. So that's what this is doing. And once you've selected the action on that, you need to update the reward. What is the consequence of performing that particular action? Does my slack get worse? Does my power get worse? Does my slack get better? So what we do is we create a reward function here based on the action taken, and it's computed by the difference in the Lagrangian objective functions before and after taking that action. So the RL framework completely stores the state, which is the graph, the next state as a consequence of the action taken, and the corresponding reward for that action into this replay buffer. So you do this multiple times for different actions, and you get a large data set of state, next state, reward, action. And you use this data set to then train the agent over here to select actions that maximize a reward. That trained RGCN agent can then be transferred over to different designs or can be further fine-tuned for different designs to maximize this reward function or select gates that can best maximize that are best for select gates and the sizes of gates that can give us the best solution to that optimization problem. So we've used this framework known as DQN in RL to train this model. And what we show here is that before we had this curve for without IR drop, we then get a red curve of the power versus delay curve with IR drop annotated. And by using our RL ECO training approach, we're then able to move this Pareto optimal front of this power versus delay curve a little bit to the left here and closer to the curve without IR drop annotated. We also compare this RL approach with traditional Lagrangian baselines, and that is shown over here. So the LR baseline is shown over here, the RL ECO training is shown over here. And what we're comparing it is in terms of percentage power overhead savings or the amount of power that we were able to recover or power recovery. And that is shown by this metric over here. We noticed that this RL training framework did the best compared to an LR baseline and compared to certain other baselines that we compared over. So that's what we showed over here. So to conclude this talk, what I did was I presented 3 different approaches on how AI can help with automation. We showed how we have these chatbots and EDA tool agents to help with automation of physical design tasks. I also showed about how AI can help with analysis with image-based AI, IR drop, and thermal analysis. And I also showed how AI can use graph-based AI for optimization of the netlist. particularly in the context of this ECO problem with IR drop annotated timing values. And notice what I wanted to convey is how different modalities of physical design exist. Physical design data can be found in the form of text, reports, scripts, can be found in the form of images, it can also be found in the form of graphs. And all of these together is why what makes it really interesting for AI to be applied, because AI has found successes in all these three different modalities as well. So, with that, I would like to conclude and stop over here. I have to acknowledge all the students in my group who've contributed to a lot of this work, collaborators at University of Minnesota, NVIDIA, as well as NYU, and of course, sponsors, research sponsors, NSF and SI2. So, I'm happy to take any questions.
So thank you very much, Vidya, for this very nice talk. So I ask to all attendees that want to put questions to include it in the chat as soon as possible. So waiting for some more questions.
Sure, absolutely happy to answer any questions. I can also go over slides,
Yeah.
share the slides if needed as well. I noticed somebody had asked if I could share the deck. Yes, I can share the deck.
So to see the evolution of the tools and so on, do you also use some visualization tools to see how the algorithms are running?
Do I use visualization tools?
Yeah.
Yes. So quite a bit. We have a lot of these AI techniques already have uh, inbuilt visualization tools to see how these are running. Open Road has a really good GUI. All of these techniques have been applied within Open Road to some extent. Open Road has a really good GUI that allows you to visualize how these optimizations are working at every step, in fact. You also have existing RL based optimizers to see what's happening at every step. Existing RL based Python inherent visualization tools to see what's the consequence of every action of the RL agent. Um, of course, just regular matplotlib to look at images and analysis of image based data. Yes. So those are the three kinds of visualization techniques I would say.
Okay, thank you. So here a question by Ulysses
Sure.
Mafazioli. Thank you for the great talk. Do you believe that generating hardware from natural language descriptions could become the future of circuit design?
Uh, so there's been a lot of recent success. I think I had this slide that had a lot of papers on generating RTL from, yeah, generating RTL from natural language. I think in really small tasks right now there has been immense success. Like if you ask um, Chat GPT to write a RTL for detecting a sequence, things that we learn as undergraduate students, or writing an FSM for a vending machine, or writing a test bench for a specific RTL, you'd find that there's been immense success in those kinds of problems. There's a lot of research in this space that's generating benchmarks, that's generating models for this. To your question on do I believe that generating hardware from natural language would be the future? I'm optimistic about it, but I have no answer yes or no because AI itself has been evolving so fast. 4 years ago, I was looking at image based AI to do this particular task here. So yeah, this is what I was looking at 4 years ago, and I would never think that in the next 3 4 years there'll be large language models that do so much for us. So it's very hard for me to predict what's going to happen in the future, given how fast AI is moving. So I'm optimistic that I feel like there would be AI assisted generation of hardware, not completely by AI itself, but AI assisted. I am optimistic about that. Yeah.
So I see no more questions here. So one point that is related also with the work that we are doing is that, as you know, nowadays many chips are designed using standard cells libraries. No? And the standard cell library, the number of functions are quite limited. No? So these circuits, in general, are using much more transistor than is needed. No, how you think that AI can help on this issue? Because to be able to really optimize at the logical level, for example, we need also to be able to have tools to do the layout of any function.
Right. So the question here is that standard cells are limiting to some extent,
Yeah,
uh,
they are
and
standard cells are not provide a real optimized circuit.
true, true. Um, so maybe there is scope to go down to transistor level. I haven't seen a lot of work that does that because we're so looking at always standard cells and how physical design relies on the fact that there are standard cells. So I haven't seen a lot of work that takes that uses AI to go down to figuring out what is the right kind of grouping of transistors in the most optimal way possible to reduce the limitation of what standard cells provide us. But perhaps it would be a really interesting logic synthesis problem where that AI could find clusters or find different kinds of logic to create the right kind of standard cells based on the logic within the RTL, and not really rely on the fact that there's an existing standard cell library. Haven't seen such work, but maybe.
Okay, so thank you. I see no more questions here in the chat. So thank you very much again for this very nice talk. I hope to see you in person in the near future. And I also just would like now to reinforce the invitation to attendees that if you lost some of the already done CASS talks, you have all them available in the YouTube channel. Sometimes the YouTube is not so good to see the last presentations, but if you do a search in the YouTube channel, you are going to find all of the about 150 talks that were already done. And soon we should announce the next CASS talks. No? So thank you to all attendees, and also thank you again to Vidya. And bye bye for you, and have a nice weekend.
Thank you so